We have given you the today's experiment list also. One is agriculture IoT, and this is also part of agriculture IoT. We are trying to monitor the conditioning of FCI godowns using IoT, because you know that the FCI godowns right now has no monitoring process. They just dump it, and they are rats or rodents or insects and all. They try to move around, the water will flow around and all these things. So we want to make it semi-automated in the FCI godowns, and with that we are trying to look into how we have to look into the IoT for that godown purpose. Okay, next. So if you try to see the you can say the goal or the aim of the project is the rice godown monitoring system based on IoT sensors and device to track and regulate essential conditions for the rice storage system only. It is not for general purpose, only for rice storage, because you have seen that mostly the government will try to buy the paddy and then keep it up and then send to mill and get back, and all these things they will try to do. So we are trying to monitor 4 parameters directly: temperature, humidity, light, and airflow. And we are trying to use some conditions like a hardware part. But before going to hardware part, I'll show you a simulation path where you can use one simulator called as there is a network simulator for IoT and sensor networks. You can use that Quantiki Collect. So there is a Quantiki software available. You can just simply take it and simulate your network, IoT network or sensor network. So we are using that Quantiki software, and there is a simulator called CUSA. So you can just simulate it and you design your own system and get the energy analysis, power requirement, everything over there. So here we are trying to use some IoT modes, like IoT modes means it's a hardware device like Skype, Arduino, like Arduino you have a Skype modes, which we are trying to use for sensing and find out the previous one. If you try to see, the previous one better. So if you try to see, these parameters are tied to Quantiki mode. Right? There is a hardware, Quantiki Skype hardware. To that we have attached these parameters, and we are trying to monitor it. Next. So this is, you have to define some of the modes as sender, and some has to be a gateway to collect it. Right? We have the nodes as senders. They send the information, temperature, humidity, airflow and all, and we are trying to collect it and see how the network runs. So next. So this is the FCI godown. We have placed around 30 modes around the FCI godown, because you know that godowns are very large. It is not a small room. So from one end to other end, we have placed around 30 sensors. 37 nodes have been placed around it, and we have kept some nodes. We have defined it as gateways, which tries to collect the information, and the other nodes will try to participate. Whenever they detect something, only they try to participate. So it is event-driven type of network. It is not continuously monitoring it, because for continuous monitoring, we need a lot of energy for that. So it is event-driven. Whenever you see a rat or something moving, it detects, or something flying, it detects, or some moisture is there, it detects. So there is a Skype's web sense, so you can simulate temperature, humidity, light and all, and you can use that SHT11 sensor only for that, and you can output it also. And there is some function inbuilt into it where you can visualize what is happening. Like earlier I have shown you the sensor nodes placed and how the packets are being moved up and down and all. So you can see the packet movement also, how they are moving around and what they are transmitting and how many packets they have transmitted and all. Okay, next. So we have simulated that, and we are collecting that information again in Quantiki, and then we are trying to see the packet loss and energy consumptions and all in that network. So this is how the impact of the connections we are seeing, which node is transmitting to which one and so on. As we see graphically, the packet movement is going on. This is the central node to which everybody is trying to send it. If they don't have a direct connection, they go via some other node. right? If the distance is far away, they take from other node and come to the collecting node and so on. So this is how the nodes are trying to communicate. You can see the node 2, node 4, node 6, and all, they are trying to, node 22, and so on, they are trying to communicate. And you can see how the packets are flowing in from one direction to other direction, and they are being collected. So here you have a sensor map, and a node control also is there, where you can define the node for the parameters what you are trying to monitor, and the network graph, how the nodes have been laid down, how the nodes are communicating, you can see it. And you can have the power analysis, and the console is also there where you can monitor everything also. So this tells you the power consumption in the network. So the green one is LPM, the blue one is CPU, and this is radio, and this is radio transmit. So the power consumption, if you try to see, the yellow one will tell you how much the power is used in the radio transmission. Right? This is the radio transmitted of the 30th node, and you have the green one is listening time, how much energy you are trying to spend in listening it, and how much you have been energy you spent in transmitting, and how much your CPU has used it, and your LPM is using it. So this is something like you can know how the nodes are being, energy being consumed. So you can see there are some nodes which are not doing anything also. Minimum energy, they are in a sleep mode, are spending minimum energy. So these nodes will be like something in the corner or somewhere in the middle, which the neighborhood is sending it, so they are not participating in it. But if you can see, there are some nodes which are contributing more, which have to do multi-hop. Like the node, they are pushing it to somebody else, and they have to do it. So they have double energy consumption and so on. So this is, again, the temperature measurements. You can see all are equally placed, and they are spending equal. They are having the uniform temperature. The temperature in the FCA godowns are almost uniform in nature. They are not varying. Right? And why it is so? Because if you try to see the FCA godowns and all, they don't have windows and all. They'll be all tight packed, and the distribution will be uniform. If they have small windows and all, then there'll be a flow of it, and you can see the variations in the temperature. Yeah, that's about the quantity software, and even so this is the file, and this is what CUSA look like. You can see how it is being transmitted and all. You can simulate and show these visuals also, how actually the packets are being moved in the network and so on. Yeah. So the 37 is the node which is trying to collect it, and sometimes they are moving it. Once the energy is over, then they move to some other nodes and so on. So you can see the sensor map and the network graph. So at that time, this is the network. Next time, this is the network. It tries on the nodes which are participating only will try to form the network. Yeah. So venakela network graph. Inka node control. Inka inta mundu page kellera back. Kaad mee slide lo. Inka back kella. Inka. No. Ido diagram. So you can see here the way the nodes are trying to connect. It will tell you whether you are directly connected or you are going through somebody else also. That's what we are trying to see over the period of time, simulatorically. So you can see that this is the collecting node, and mostly we have kept only star topology. We have not kept bus or something else. You can define the network structure also. It is one hop only. Mostly we are trying to see that it goes one hop. In case, worst case, when the node is here collecting and some node is here which cannot reach, then they go by a hop. Yeah, sensor skill. No, here we can see that they are mostly star connected. They are not going in multi-hop connections and all. Next. And the temperatures are also uniform throughout from 1 to 30. All the nodes have the uniform temperature around it. So this is how the network hops are moving, 1 hop, 2 hop, 3 hop, maximum it is going to 3 hop. Otherwise it is remaining at 1 hop only. Mostly they are in 1 hop. At times they go to 2 hop and sometimes they are going to 3 hop. That's the maximum thing which it is trying to take. And this is the received packets per node. First node have received 3 packets, the third node only 2, and so on. So last 5 minutes, if you try to see, those are the things. And this is the power consumption on the nodes. Each and every node, you can see how the power is being consumed. The average powers are coming up, yeah. And that is in milliwatt. So if you have a battery of some 1000 joules, you can know how long this node can survive. And this is the duty cycling, we call it as radio duty cycling. We can see that the red one is the node is listening and blue is sleeping. Blue is transmitting. So we have not kept any sleep mode over here. They either receive or transmit. So most of them they will be in receive mode, and the blue thing is they are transmitting. So you can see the transmitting is very less and receiving is more. And this is instant power consumption. Every instant you can see how much power has been consumed. And this tells you completely what is happening inside the network. This is one thing which we can do it before actually we put the hardware in the godowns and all. Right? We can analyze, like if we put this type of battery, how long it survives and what are the locations which is good and so on. So now you can play with the locations also and see that the energy consumption can be reduced. And if there are more number of sensors, you can reduce them also. You can switch off some of the sensors and see how the power is being consumed. So if you know the ideal places, then going there and installing will be much simpler. So this is one simulator. It is free of cost, and anybody can download the Quantity software and try to install it and see it. And they can define their own modes also. Here he has used the Skype nodes. So we can see the complete analysis of how many hops, lost packet, dropped packet, received packets. Complete analysis we can know. Like if you have a network, if you transmit it, whether the packet has been received or dropped or lost, you can easily find it out. And this is very good if your network have a user density more. If it is user density less, you will not have any dropped packets. Right? If the number of users are very less, there is no question of dropping the packet. If the number of users are more, then we can really see the drop of packets. Right? Okay, that's about the software and simulator, which if possible, I think you can use it as a lab simulator and you can use experiments on that so that the people knows how to see a MAC layer and how many packets are being dropped, how many are being transmitted, and what is the power consumption. These things they can easily understand. Okay, so we'll stop about the collection of data and how to simulate it and all. And we'll go to the agriculture AI. Oh, in the చూపిస్తారు వెబ్సైట్స్ డాట్స్ ఇది దిస్ ఈజ్ కిందకి వెళ్ళండి యా కిందకి వెళ్తారా సో దిస్ ఈజ్ వాట్ ది ప్రోగ్రామింగ్ పార్ట్ లుక్ లైక్ వాట్ వీ హ్యావ్ written the program for that application. So we are trying to find out temperature, humidity, light, pressure, and these three, and we are trying to put it in a file and try to find out the averages of that and then trying to put it on the graph. Right. So this is the raw humidity and how to find out the humidity offset, and depending on the SH11 sensor we have picked it up. So this is the code what they have written it for the request time and all these things. Yeah, in that you can program it. You can write the code and you can modify the code and all. Yeah, C language. Python also it takes. C basically they have written the quantity for C because it's a older version. It is more predominantly for the C. If you want, we can share the file also for you. Right? No, దాన్ని modify చేశారు కదా మీరు. See, there is a source code available and it has been modified for that. So, ఇంకొకసారి రన్ చేస్తారా? Yes. రన్ చేయండి కోడ్ ఇది సిమ్యులేటర్లో సిమ్యులేటర్ వేరే పెట్టండి, సిమ్యులేటర్ పెట్టండి ఒకసారి. సిమ్యులేటర్ ఆన్ చేసే ఉంది కదండి, ఆఫ్ చేశారా? ఓకే, యా యూ కెన్, యా you want to start? Yeah.
Earlier. So now we are back. So the last slide was talking about as a multimodal communication behavior, which essential talks that, okay, in visual, what are the behavior, the different kind of communication behavior you can find, started from just gesture. Two people can just talk to each other using gesturing, and gesturing could be either head, eyes, and arm, different kind of gesture. Then body language, also eye contact, head gaze, eyes gaze, just kind of looking somebody, staring at, those kind of things. Similarly, vocal also, you have a different way you can communicate, behave in under each categories. And it is verbal communication, this could be just using words or part of speech, okay, and discourse acts. Okay. Here you can see that the communities means people that is engaged in certain behavior, in certain mode, certain sensing activities, sensor activities, and as a speech community of all kind of communication. In vision, it could be just one-dimensional, or it could be video, it could be static, image, all those kind of, including all this behavior you saw on the last slide. Then multimedia, we have got both audio, video, and other things. We'll talk later. Now, the communities essentially says, okay, they explore all potential mediums, all potential sensing activities. The community is not just user, they could be also research community too. Okay? Here is an example that multimodal human-computer interaction, or HCI, how it is possible. Even you can set up an experiment accordingly. As you see, here is the person, okay? Here the person sitting here, let's call user. It can have various type of communication, which essentially will be combined here. Now, let's think about a speech. A speech synthesizer, it gets the fixed pitch mapping. At the same time, it can switch between these two ends, and here you can get multiple mediums, multiple sensing activities, okay, such as a vowel network, consonant network, and your VIC decision networking. Everything combined can go here, or a contact switch can be available to fixed off mapping. And that also is possible. And you can modulate that using a pedal control over there. Okay? So all you can see here that it shows how to design and evaluate a new computer system where human interacts through multiple modalities. It's just a framework, is a emulating framework. Both input to and output modalities could be combined or could be presented. Okay? Now, a neural network interface is also possible when you try to do some data processing over here. Now, we need some rules or models. These models there are many models, but more popular models in this area are hidden marker model. In the hidden marker model is typically you can predict something. You are following certain pattern, then you can predict based on the pattern. Okay? And there are two kind of hidden marker model. Is a factorial hidden marker model or coupled hidden marker model. Now, in this case, you go for multiple state variables to represent the hidden state. Okay? Now, for example, you want to, for traffic, and this is something actually we know already that this weather modeling, traffic modeling is being done in the same process. Now, more additional models are being used in this area for multimodal computation, which are ANN, backpropagation, or simple CNN. Okay? And under this, for this multimodal computation model 2, you have, hope some of you heard about dynamic Bayesian models being networked. Okay? Then there's a reference actually, if you don't know, it's a very powerful model being used in many disciplines. Then Kevin Murphy's thesis and MATLAB toolbox gives very details how to implement things. Okay? Then this is an example showing okay, how audiovisual speech segmentation is possible using artificial neural network. Not that we are solving it, but kind of giving a feel that you can use various models, ANN, CNN, segmentations, as well as dynamic Bayesian networks. Okay. Now, how deep learning can be used? Okay. Now, one thing I can make it clear to you that whether just machine learning or your DNN, they are typically representations. So, representation is a term that said that how you can take the problem, represent in certain way, okay, and any media, any modality can be modeled using that. Essentially, the modalities, multimodalities, they could be imposed in representations. And here, your DNN is a typical deep learning, is a representation for multimodal applications. Okay. Now, it is possible that because you are using an abstracted deep learning phenomenon here, now large-scale multimodal data set could be printed by that. And to compute that, knowing that deep learning has a lot of computing overhead, you engage GPUs for getting the abstraction of the data. Okay? And high-level visual features are possible just taking the result into a visual format. And multidimensional linguistic feature is also one of the attractive feature or a key enabler for the multimedia research. So what we told there, it's kind of a representation in general, but this slide is going to show you the real-world problems by multimodal research. Now, if you look at people's face, different kind of face, disgusting. This face is a kind of anger. So various emotions. Okay. Similarly, you can have a persuasion type of show and the personal traits. Okay. Now, in a way, why I'm showing this to you? Why it's important? First of all, definitely it's real things. Now, suppose you want to do some emotional analysis. Okay, you want to see somebody is going to the shopping. Camera is given there. Customer is doing shopping, and when you buy something, suppose buying a cloth, you may like it, you may not like it. If you don't like it, sometimes body language, emotions, they express that. So it's possible that somebody can watch it, can know whether this person is going to buy it or not going to buy it. Okay? So this is just one example. There are many examples you can think about how emotion could be used. Similarly, a patient is in pain or is comfortable. From facial expression, you can see that. Okay? There are many scenarios you can always think. Similarly, pursuing. You can even know whether when you talk to somebody, you can pursue from the expression, from the gesture, you can know, yes, I can pursue further to get my things done. Okay? It's used for business negotiations and dealings, contract dealings. And also, media descriptions. Given a picture, they say that picture is a description by 1,000 words, okay? Better than 1,000 words, okay? Now, from each you can say this is a place, is a play home or kind of play schools. Okay, somebody is in accident or playing. So given the picture, it is possible to get things described. That's where we started. That okay, if you have got at least two inputs, then you extract feature independently. Then you combine them. Then you can figure out the background about the event. Similarly, you may not have image caption, but you can create an image caption. If you're a novice news reporter, somebody gave you a picture like this, you can always come up with a very beautiful image captioning. Okay? Similarly, video captioning is possible. You play the video, then automatically captioning will be coming up. They are actually smart technique of using various tools that we have and abstracting it given the video or image. Okay? And sometimes also you can get a visual question answering the same way. Another example or problem is the event recognition. Okay? Something what is happening in each case. Somebody is doing yoga, or somebody is trying is cooking. Things are what is happening. Now that's possible using either recognizing the action and segmentation. The two sources you can use it to find it out. And multimedia information retrieval is another area. So given some images in past without details or details mixed off, you can recall that as content, then you can always find it out. So the real problem to tell you that, hey, here are the amount of work involved there. Now, there's a nice paper with this reference. Okay, there are on multimodal machine learning. There's a survey paper. So, with the details about representation, alignment, fusion, transition, and co-learning. I thought these are the challenges of machine learning, I guess. Okay. Challenge 1. I think something is mixed up here. Yeah, something is missing here. It should be challenges. Okay, challenges. So the challenge 1 is representation. Okay. Now, we're talking multimodal representation, right? So the definition is learning how to represent multimodal data in a way that exploits the complementarity and redundancies. Let me read it again. Learning how to represent multimodal data in a way that exploits the complementarity and redundancies. Look at this plane. Okay, let's say we want to capture something, a surprise, or some word like, this is actually, what is this? Using visual, right? Then somebody says, wow. They both, two sources, they tell the same thing. Okay? And somebody says, I like it. Giving consent, good gesture, okay? And from the face also you can do the same thing. And you can hear the tone. A written text, a tone, joyful tone, and from the expression. You can confirm more than 1, 2, 3 sources that say the appeasement, pleased, okay? And here, scary, a tense voice, and from face expression. So there are two modalities, they can be combined together to express a different emotion and different things, okay? So what to do actually is given here. I'm sorry for the blur diagram, so probably I have to take care of it later, okay? Now modality 1, modality 2, okay? 1, 2, could be 1, 2, 3, 1, 2, okay? They essentially are together get a representation. Or a representation could be combination of 2, either way. Second challenge is alignment. These are multimodal challenges actually, and how to resolve to some extent. alignment definition is identify the direct relationship between elements or sub-elements from two or more different modalities. Just like you saw there, previous one, this is one modality, this is another modality. There are three modalities here. Same thing here, how do we align them? Why need alignment, by the way? To find some commonness. If you align them, you can say, yes, they are of same category. They can conform or complement each other. That's complementarity, okay? Complement each other. So you have, say, modality 1, you have components or sub-elements. Modality 2, you also have many. You have n here. Not necessarily T1 is aligned to T2. T1 is for T4, T2, T5. Some way you can find alignment. As long as you find a good number of alignment, then a representation will be good. Now, explicit alignments. The goal is to directly find a correspondence between elements of different modality, which the picture shows here. Okay? I call that fancy alignment or whatever, right? Then implicit alignment uses internal latent alignment of modalities in order to better solve a different problem. So what is the difference between these two? One is direct, one is implicit. So it means you have to extract those things. After extraction, you can find alignment. The alignment could be already exposed, or you have to find it. Look at implicit alignments here, example. Now let's say, look at the word. A dog with tennis ball is swimming in murky water. Okay? Now, in this picture, you see the tennis ball. Okay? Tennis ball is here. And there's one dog. Now, if you look at these two words, tennis ball and dog is gone, then swimming in murky water. So swimming is happening, and swimming is associated with the murky water. So you are associating, aligning swimming with water. You cannot swim in the air. You cannot swim anything else. Okay? So that's basically alignment. And it's possible that we can have a ball, just ball picture there, and with dog holding that in the mouth. Okay? Now, you might see a picture, but you want to find out alignments. Okay? When you write something in a text, and you try to, a text is one representation or one modality, and picture is another modality. So that way you can find maybe part of them. As you see here, you are not able to see everything, but that something is able to match. The fusion means putting together, joining. So fusion definition is to join information, putting information together from two or more modalities, okay, to perform a prediction task. Now, again, you can have a early fusion or late fusion. Now, the model agnostic approach, okay, in spite of model, without model basically, okay, is in early fusion you get two modalities, 1 and 2, okay. You try to merge them, and a classifier is applied there, like clustering or things like that. You get them, okay. And late fusion, you apply the classifier at the input like this, then you merge, you basically go for fusion. Fusion means combine or join. You combine, before combining you classify here. Both modalities have been classified, then merged. Here, both are merged, then classified. Okay? And then you can compare which one will be better in which scenario. Then a model-based, this is model agnostic means without model, just common sense. But this one is actually using model as an intermediate approach. You can use deep neural network, you can kernel-based methods or graphical methods. Okay? So these are again representations. Then you can find out different views, some views here, some views there, with this, and say which one is more of, working better. Translation. Translation is a process of changing data from one modality to another. Just like language translation, for example. And representation could be in one language, not representation, the input could be in one language, one modality, say Chinese is one modality, Hindi is another modality. Okay? Now you have to translate them, and before translate sometime you have to find the relation. So how translation happens? They try to find a relationship, and they find a pattern of relationship. That's called a feature, or you can say underlying kernel. And more they see, they can find how language translation happens. They can find those key points inside hidden in when they have millions of translation, watch it, observe it, they try to find out those things in translation. And they build actually a rule that is essentially going to help. Now, sometime it could be model-driven or just example-based. Example-based means in such small sections, okay, this is source, then this is target. That's how the translation happens. Another source goes to target. And these are the, what do you call it, repetitively observe when you break those two languages and try to find relationship, translation relationship. Okay? One is a source, blue color, and target. Source to target is a phenomenon that is observed or underlined or hidden in a translation between any two languages or image to language, could be anything possible. Okay? Now, another one is called model-driven. Okay? The difference is what I told here, that you can pretty much go and find the rule using, suppose, your DNA or something like that, then that actually is model-based. When you don't use model-based, you try to get a small piece and said, I give an example, I notice all the time, if I'm starting with this, it relates to that. And this is a pattern, example, repeatedly observe. That's why it's called example-based. And this is model-driven. Obviously, example-based has a lot of limitation. For large-scale remote languages, is it hard to get. But model automatic process which can be feasible by any manner who want to implement it. So for this, you may have to do first training, then using the kernel of that, then go for the translation. The fifth challenge is co-learning. Co-learning refers to transfer knowledge between modalities, including their representations and predictive models. So two things, both representation and models. So you have modality 1, modality 2. You may have a way to compare them or set them, put them in framework, and get the prediction from each of them. Okay? Now, given the modality essentially is having hidden data. Okay? Now, from data, you always get knowledge. And you find actually knowledge, there's some common knowledge you might be finding between them. Okay? It's about at what level you are trying to get that. And to get that level, typically you try to learn, you have to learn the existing modalities well and derive knowledge. And to get the knowledge, basically you go for a learning mechanism. The word co-learning here because you are trying to learn from both the modalities. Okay? It's same example saying that, okay, you can do learning using given data set from like parallel, at the same time try to find the through co-learning between two blocks here, and here non-parallel. Some scenario may not allow to do parallel, then non-parallel means you can basically skew sets. Dot dot means not straight line, they're kind of connecting other ones. Then another one is hybrid. Somewhere it is direct, somewhere it is non-parallel. That combination is called hybrid. Now, keeping everything together, that's called taxonomy of multimedia research. You have a representation such as a graphical model, neural network, sequential, similarity, structure. Okay, these are your representations. Okay, remember this thing. Okay, because we will be using it towards in slide. Then translation, retrieval combinations, model based or example based. Then alignment, explicit, implicit, fusion, early fusion, late fusion, and hybrid fusion. Or could be model based. This is model agnostic, is with model based. And we just discussed about co-learning. So it's everything putting in one slide. And this is an interesting table where you can watch, you have representation, the challenges, representation, translation, fusion, alignment, co-learning, and here you have some of the applications. Speech recognition and synthesis, event detection, emotion and affect, both recognition and synthesis, is action classification and multimedia event driven. Media description, for possible subcategories and application. Multimedia retrievals, either cross-modal or cross-modal hasting, retrieval and hasting. So if you see here, all of them have some representation, possible to do representation, all of them. See? But when it comes to translation, all of them are not, all applications are not suitable for translation. Speech recognition is one doing it. Emotion, yes. Some media and some multimedia retrievals. Similarly, fusion, not everything but some of them. Alignment, some of them. So one can actually justify these things by thinking a little bit and checking why translation is not here. Not here. Okay? Okay, we did some basic discussion about representations particularly and challenges. Let's go to the real multimedia IoT elements. Then we jump into actually multimodal computing, the rest of the slides. Now, here, what is this called? MIoT. MIoT means multimedia IoT. So, to process multimedia IoT, what do you need? Element means you need. What are the processing entities you need? So, what you need, the first one is identification. You have to, any data is coming, you have to identify it. An object is coming to identify it. Okay? Then, after that, you go for, what is this, physical object? I can't read that properly, that's kind of so blurred. Yeah, physical objects. Okay? Identification, physical object. Third one is communication. Fourth one is middleware. Fourth one is, yeah, essentially this is the key. This is the key we will be focusing, because you know already these things. You know this. All these three things you know. You may be knowing something, but I will clarify this. But you know this thing, physical layer, you know this, communication, you know this thing. Middleware also, we know, but I can always talk about it a little bit. Then this is the one that we are supposed to discuss in detail. Then application also know it. Take one of them each other. So what the first layer was identification layer. So identification layer means we are talking about multimedia IoT. So multimedia IoT is using some objects, some gadgets, be it a camera, a sensor, or be it another type of sensor. We call it sensor and object interchangeable, I am calling them. So all those things you buy, they have a ID tag, all of them. What we call that? We call that EPC. Every electronic product has code. Okay? But what happens is these products, when you buy, they not necessarily change the EPC number. Suppose you have got 3 or 4 objects, they will have same EPC possibly. But if you have only one of each type, then that's fine. Your EPC will be unique. But also sometimes you get actually U-code, ubiquitous code or U-code in general. Now, if you find there's a kind of confusion or repeating, all you can do is, since each of these electronic products, they are a part of your wireless sensor network, they basically equipped with that, then they could be either IP4 or IP6. Then, which means you can identify, you can provide a tag or ID using that IP number, okay? IP address, because IP address is always unique. So which means you have 3 choices: EPC or U-code or IP address. So that's how you will be identifying each object involved in the identification layer, bottom layer. So physical object layer could be either scalar objects or multimedia objects. Okay? So because the physical object layer with the multimedia IoT is responsible in collecting data from various objects within the network, then and transmit that to central repository for further processing. So we classify these objects either scalar object or multimedia object. So what is scalar object? Scalar objects are typically characterized by single modality. Okay, single modality could be just maybe vision or audio, those kind of, or text, just one. Whereas multimedia object may be single or maybe multiple modalities. Think about a video frame. Video frame is having is both having image as well as speech. But an image is just a single modality. It's a multimedia object, but single modality. But it is multi-modalities. Then the characteristics, to characterize the objects with the different modalities is a characteristic of the MIoT, which is different from traditional IoT. So what is saying that to characterize, depending on scalar or not, we have multiple objects, but each object has a unique identification, and each one also belongs to certain modalities. So we pretty much tag them together, we characterize this ID, this modality, this ID, this modality. And that way it will be easier for doing management and the processing, data collections. In communication layer, within the MIoT, a same function as a traditional IoT that we discuss in sub-layers like link, network, and transport layer. Okay? Now, and these components essentially also support the MAC protocols, okay, and different topologies. And typically we use star topology, and star topology is used to connect the full function devices to reduced function devices. Okay? But mesh topology, in the case of mesh topology, they always connect the full function devices. Basically, in a device world, when trying to do connection, you will always find some are having full function like OS and other analytical computing facilities, or some could be just passive, just passing data. So star is useful to connect the full function to reduced function. You may have a reduced function at the edges and a star could be full function. But if it's mesh topology, then all of them are full. And we discussed earlier that you can combine mesh and star to make it more scalable. Then the network component for connectivity and routing within a IoT is similar to the previous discussion. And this is the very popular discussion for these routing protocols. Okay? And you can have, it's exactly the same thing that we discussed in the network layer. Okay? Now, only thing is you can think that, okay, the transport components for end-to-end communication provides a flow and a congestion control mechanism. Okay? We did not discuss these things because that time it was not very important, but now it comes to surface that, okay, for a IoT, okay, we will having both the environment with a low power environment and UDP is always there. At the same time, if that is possible to do this flow and congestion, then that control also, just like regular wireless network would do that. Okay. Middleware, okay. I told I will be giving some little bit stress on the middleware layer because we didn't discuss in particular what is the middleware layer within a IoT. So middleware is basically a software layer between network communication and operating systems and applications. Okay. Now this layer is sometimes kind of a computing algorithms in a software simulation ways. That is, this middleware layer allows IoT applications. It is more towards application side, okay? Application for heterogeneous objects that is to be developed without needing underlying hardware platforms. So we don't need hardware platform, though the nature of job is kind of as you compute with the hardware. So that is actually fulfilled using a software layer, writing simulation like for that. Then middleware service components can be classified as a functional and non-functional. Okay? The functional component include resource discovery and management, data, event, and code management. So what is saying that, okay, when you talk about implementing functional middleware component, you don't have to use hardware, but all those algorithms kind of take the data, do certain things as we do computing, doing simple manipulation using software, okay, and apply to scenarios such as discover resources, which are the other agents available over there, then how to manage data, okay, how to manage code. So typically these are all MATLAB-like stuff you can do even using software. Examples of a non-functional requirement is scalability, timelines, so which you handle like using two types of as you discussed that you have a star and mesh network layer, but then it has to be supported by some tools or software. Okay? Then timelines, putting timestamps and making sure that the communication happens, acknowledgement happens, those kind of things also, they belong to non-functional requirements and including even security services. Okay? So in summary, the middleware layer is a software layer try to fill the gap that you don't need to have a hardware, but still you can achieve a lot of management functionalities. And this is the more important thing that we'll be going to discuss soon. Now, typically, this layer serves as the processing layer or computational layer in traditional IoTs. It has hardware components such as a microcontroller, FPGA, system on chip, and also software, real-time operating components. like tiny OS, Contiki, and so on. So for multimedia IoT, the third software component is included, that's called data analytics. Okay. Now there could be other computational component just to include cloud platform with the servers and some smart object, okay, or could be intermediate nodes also, but typically we use the cloud for processing the data for real-time computation if the operation speed is not compromised too much. So we'll look into how this architecture is taken care of. Application layer again, the same thing using co-op. Okay. Now, this is a summary actually what we discussed last several slides is the summary of the table is the summarizing whole thing. Okay, identification layer, we talk about that, EPC or IP, IP numbers, okay, IP addresses. Then physical object layer, we discussed about scalar or multiple, it could be multimedia objects too, both single and multiple modalities. And everything is the same, repeating, basically summarizing it here, except this layer. So this is the layer is a new. All of them are just there before. We just try to review it quickly. But this is except the middleware layer. And sometimes it's there, some not there. But we are going to talk about this particular layer. Okay, that's actually that layer. So if you notice, you start with the identification layer, physical object layer, communication layer, then middleware layer. Remember that? Did all those things from here to here, middleware. And application layer is there also, you'll see. So this is what we are trying to fill the gap. So you have got 4 stages here, application layer here, the rest of them here, all these things is actually for the big data processing or multimodal big data architecture for MIoT. Our purpose is actually to process the data analytics for multimodal inputs. Yeah, we cannot go and come back to this thing while we discuss each of the areas. Now, multimodal computing layer is a layer to perform data integration. First is a summary, then we go back. Okay, so this architecture, okay, is composed of 4 functional units. Okay, 4 functional units. 1, 2, 3, and 4. Okay, what are they? Data centralized unit, multimodal data aggregation unit, multimodal data divide and conquer computation unit, and fusion and decision making unit, 4 of them. We'll take each of them and see how they coordinate with each other or what happens in each case. First to take the data centralized unit. Let's go to the picture and take a good look at it. Can you see this thing? Can you see well? I can see. I don't know. They're so small because I have a small screen here. That's why I'm not able to see that. Okay. Now, you see here that each object 1, object 2, object 3. This is multimodal. This is single modality, like image. This is single modality, scalar. So that's what we discussed earlier, right? The 3 categories are there, okay? And maybe repeating similar instances later. And there's a data bus over there. It takes its input from middleware layer, and these are the type of objects we are getting, and that has to be, this data has to be centralized. So let's see what happens here and how much data is processed for what. This is the one, right? The data centralized unit process raw data from various objects. We saw 3 different kind of objects with their own identity. They're unique. And these objects can be scalar, multimedia objects, and multimedia, both single modality and multiple modalities. Then it performs the data integration, data cleaning, data redundancy, elimination. So essentially, when you get data, raw data, it comes with a lot of sometimes garbages, additional data of no necessity. You don't want to take them up because they will unnecessarily waste your computation. So you have to identify them and eliminate them. Data cleaning, same thing. Sometimes you got a lot of zeros, lot of unnecessary ones. You have to clean those things. Okay? So data integration processes, you combine those different data from different objects and cleaning them. What else? You also combine the object data with their unique identity. Since you know that each object has an identity, you can say, okay, this is the data from this unit and so on. For scalar object data or multimedia object with a single modality, no data separation is performed. But, okay, no data separation is performed before combination of unique identity. So that means you first find identity, then you combine. For multimedia object with more than one modality, the third category you saw there, data will be pre-processed. There is no pre-processing, it is pre-processed. I mean, what happened in pre-processing? You arrange according to the modalities, what do you call that? Multiple modalities, 2 or 3. So accordingly, basically, you try to arrange them before, again, identify them. So basically, first to give identity, then find who are the models and modalities having 2 objects or 3 objects, those kind of things. After the raw data pre-processing is, what is pre-processing actually? It's arrangement, organization of that. The pre-processed data is passed to the next level called multimodal data aggregation unit, that is coming here. So let's take a look at it, and this is multimodal data aggregation unit. What you have, this is aggregation data blocks. Okay, aggregated data block. This is multimodal partition data blocks. You have single and scalar and single modality data. That was actually saying that you had to put them together, but before putting together, you have to tag them. Then this is actually similar things, but only for the multimodal modalities data aggregation. Then let's try to see what is happening here. Now, in multimodal data aggregation unit, what happens? Now, there is a need to aggregate and organize the data into proper format for further processing. How? For scalar objects or multimedia objects with a single modality, as you saw that the left side, the blue box, the first aggregation algorithm arranges the data into equal sized aggregation data blocks. Basically, they divide that into blocks, and that helps them for big data analytics. Then multimodal data aggregates the data of the same object source based on its identity and modalities, finding similar modalities together. This unit can be operated in 2 modes, offline or real time. If it's offline, then you have to store that data. Okay? Otherwise, you will pass that to the next level called multimodal divide and conquer. Okay? Now, in multimodal divide and conquer computation unit, which is let's go back and see that. Right. This is the one, right? So there's some similarity over there. We can go and see what's going on here. You should have that storage already there. Storage is for those things that are non-real time data. Right. Now, this unit contains, I think pictures are given next slide, but let's see what it's talking about. This unit contains a divide and conquer subsystem with their own computational servers. Each block, they have their own servers to process the data of each modality in parallel. Okay? Usage of the specific divide and conquer subsystem depends on the modality. So that means computation could be different from different one, but they're in parallel. Each subsystem aims to extract the target features. So essentially, each blue box there, they're actually trying to extract the target features. What is target features? Depending on the object. Visual features, image data for scalar and singular, text features for text data, audio features for audio data, and so on. And for this multi-modal things, you go for audio and visual for the video. So this is what happened actually. Okay? That block you see, you get the aggregator block from the bottom label, that label below that, and try to divide the blocks. But you don't know block size. Okay? So you keep doing it until you achieve the threshold, as long as you reach the threshold. So that's why you divide and go back, divide and go back. Okay? Then once you have achieved that, the block, optimal block, then you call target feature extraction function. Okay? And then you go for conquer function. So divide, then do feature extraction, then call conquer. We'll see what's going on in conquer. So division of block recursively, see, until the block size reaches a set threshold. So what is the threshold? You can define for different applications and call it. And you be in this process, then you can find the parameters that basically say your thresholding is to be loose or threshold is to be tightened. Then target feature extraction function is called, okay, to extract the local features. Then here's the example actually given here, okay, how divide conquer mechanism is done with the scalar or singular modality, and similarly you have also another for the multiple modalities. In say visual features like a color, texture, even that could be texture actually is coarse or fine, directivity, contrast, shape, all these things coming into texture. So color and texture for visual. For audio features, how to extract features? We generate basically audio features is based on a fast Fourier transform, we call the short time fast Fourier transform, zero crossing rate, linear predictive coding. They are all standard techniques in signal processing or otherwise. Volume standard deviation. Okay? So some of the techniques, they can be used for audio, extracting audio features. For video features, for more multimodal things, you get motion feature, motion quality, for direction motion is going up or down, horizontal or vertical, then magnitude histogram, optical flow. So you don't have to remember, but at least you know that's what's going on, so that if there's chance come for you to implement things in research, then they're all handy, but at least get an idea what is going on there. These features are extracted from sub-blocks during divide and conquer mechanism. The second one, this one actually. Yeah, this part. Now go to conquer, the bottom one. So what happens in the conquer function combines and process the features in the reverse order. First you get the features, okay, combine that, then once you have those features, you combine the reverse order. So if something coming one way, you fix it, then go for the reverse order. Okay? Now, when you go reverse order, you go just by taking the two neighbors, then move upwards. If you are coming from top to bottom, or this time go from bottom to top. And what you do, you still go for the features. So do you understand what's going on? You typically take 2 blocks, find feature, next 2 blocks, time feature, and you get some feature, local features. Once you have that, again now go back, reverse order. So by that, we can shuffling and try to get the best out of all those divide and conquer strategies. Now, at the same time, the block size, the threshold also is important. Okay, and based on the experience or based on what is going on around there, you can find this threshold is good enough for me or not. Okay. For each input aggregated data block, from bottom up after this, after the threshold, the final feature block, which contains the local features, is the result. Okay. Oops. Right. So this is essentially is going on. Okay. You partition data block, you part data separations, then you basically apply divide and conquer functions, and in parallel. See. Then after that, all the feature results is passed to the next unit. What is next unit? Fusion unit. Okay. Fusion and something unit. Okay. Fusion and decision making unit, the last unit before you send to the application layer. In fusion and decision making unit, which is the final stage of computation layer, it has feature storage unit, decision making server, and infrastructure for communication. Okay. The servers supported by various algorithms like organize, store, transmit. That's exactly what you need to do. But it's saying that you do this thing based on certain algorithms. So here research is an algorithm that you design, if perform better, then that is a good research. Okay. The decision-making servers use smart algorithms to make decisions in efficient manner. Same thing is emphasizing that. So after decision has been made, then this fusion decision making unit gives desired output so that any application can use it in real time or offline. Okay. So the final process is, did I miss a figure? No. Okay. Now, multimodal feature fusion decision making subsystem, FDMU, let's see what is inside that. It has decision level fusion and decision making fusion. Next is feature level fusion. Fusion means join, put together, right? So feature level fusion and decision making. That difference, I think that's a picture next to explain that. See. In this case, the first one, you are trying to make a decision level, this is decision level fusion and decision making. So you first make local decision, then you put them together. Okay? Decision making. That's then the output. Whereas here you do feature level fusion, then decision making. See, this is what is this? Is final fusion module here. Okay, this is final fusion module here. Okay, now this is your feature block. So what is difference? Modality 1, modality 2. You are getting D1, D2. They look same, right? No, something is wrong. No, wait a minute. There's something wrong. There should be 2 different types actually. Yeah, there's something, maybe the picture has been swapped or something there. There are 2 different, in one case you are aggregating the fusion first and decision. Other one is the decision then fusion, get the final result. I'm trying to figure out what has happened. Yeah, it should not be a different, it should be different one. If you have a feature level fusion, was I look at that this morning, that they are okay, maybe something. So, but what's the final presentation? I'll change those things there. Okay. So this is certainly going to change. Feature blocks. You have final decision fusion modules. Yeah, the same thing. It should be different. Okay, because see this, they are different. Feature level fusion and decision making. Decision level fusion and decision making. Okay, I'll check that later. Then decision level fusion, again the target, I think you can get an idea what's going on from description actually. Okay, here. The target analysis first provide local decision D1 to Dn, which is basically the left one is correct, based on the individual modality feature blocks. Features 1, 2, 3, all those up to n. And local decisions are then combined. Okay, local decisions are combined using final decision fusion module to make a fused decision vector and analyze. Now, yeah, let's go back. Yeah. So there are n modalities. They are basically coming to decision module. Okay. Then it is fused here before final decision. The second one is decision level fusion 2 by 2. Wait a minute. Yeah, the second one is this one, second one, right? That's the feature level fusion. What happens in the feature level fusion and decision making? The feature blocks are first combined. Decision was taken individually earlier, but now that will combine first. Okay, so which means we should get here, we should get a combination here instead of being separately done. Okay, this one, right? This is the one. Okay, in feature level fusion and decision making, the feature blocks are first combined, okay, and then sent as input to the feature fusion module. So feature fusion module is a module that is after the second block, which merges the set of features blocks from different modality before the decision making. Okay, and they have their own advantage, disadvantage. The advantage is it can utilize the correlation between the multiple feature blocks from different modality at an early stage, which helps the better decision making. And that's intuitively correct, because if you have the features early, then try to put together, you may get a more elaborate, rich features, and probably you can get heavy weighted features to come out. Okay, and disadvantage is kind of is synchronization is hard. You need more computation for that, and it's because the features from the different one closely coupled, and the first one is the representation. Representation means suppose you want to combine two modality, and one modality is represented in machine learning, second one is in deep learning. How can you combine that? So that's the challenge. That is pretty much, I guess. So we define multimodal examples and data for IoT, except that error in the picture, I will fix it in the final one. Briefly introduce multimodal computation model and deep learning. We also examine core challenges of deep model machine learning, then MIoT architecture, then analyzing the both type of MIoT data processing structure. No, not much example is there. They have been kind of proposed, and I don't have any example for those things now with me. Okay. These are the architectures, always the ideas, and one can, if you want to do research in that area, essentially you will be implementing the ideas. You can augment your own ideas. Okay, and it could be implemented, but at least I did not see them in the literature. Or because it could be trivial, they don't publish it. If something trivial, don't publish it. Because all they are doing is getting the modalities and converting it into small blocks, do the feature extraction, and process it either front end or back end. Okay, the only challenge that mentioned that okay, if you are combining or fusion, we call fusion. For fusion, they need to ensure that the representations are the same. The representations are different, then fusion is not possible or a wrong results. So it's not that difficult to do. Okay, so that's maybe the reason it could not be publishable. The idea is pretty low hanging. Yeah, when actually that is definite, that's a common thing. There's no scenario, this is the way it is. That's the way is all those, we saw that multimedia, multimodal is something for processing multimedia applications. Now, when you do multimedia application called MIoT or multimedia IoT, it shows there are 6, 7 layers are there. And most of the layers are common. After middleware and before application, everything is common. Only that layer is unique. Okay. Now, the question comes, what one can do? You have got, earlier it was all single objective, single modality. But now you've got a lot of single modality, scalar, and also you have a multiple modality. Now, when a single modality, multimodality coming, we are getting many sources of input. And these inputs are nothing but objects. We want it because as you saw that plane in which you different pictures, or sometimes word, sometimes sound, you combine all these modalities, then take a decision. Okay, why decision? Otherwise you cannot take decision. So they come in representations until the computational unit. Now the question is, how do I go to the application layer? Unless I do a proper computation, take the feature-rich answer for the application layer. Application layer looks for the features so that they can use it. And we are coming with many features, and we know they are connected and don't want to separate them. So intelligently, we are trying to put those features together. And that's why they divide and conquer. They have to divide and conquer because they can't process everything together. They put them into single chunks. Okay? Then once that they divide and they try to get feature, is after all this is coming from a same set of data, same representations possibly, or similar representations. So they try to collect similar representation, make divide and conquer rules, and check it, both forward and backward. Even if you do forward and backward, the noise will go. But what remains is the absolute solid features. And that feature is carried away and from set to set, or block to block, or you can say rather modality to modality. Okay. And if the 3, 4 modality is specifying a particular answer, okay, I do not know what is going here. Well, you have multiple modality, there are similarity, we did all those things processing there. Then now I am getting feature equally drawn from both sides. When they combine it, they confirm that this is the image about. Okay, so that's essentially the background. So it has to be, there's no, this when we can do that, it has to be done. It's a part of the computing process. Yes, this same thing we are doing. This is what we are doing. We are absolutely doing the same thing here. So, how much time will it take to boardroom here from here? 2 minutes, huh? Oh, that's okay. Then we can, yeah. Okay, so tomorrow we have good sources, but we are not looking translation. We are looking some questions to be answered where all the answers are there. And if my IoT has a limited domain, and domain is only, suppose I am using image, okay? Not, when I'm using, I may not be using other ones. It's another question, how much multimodality will help? We've not thought about it actually, okay? But maybe as you go step by step, we'll see there must be a way out. Okay, so, but first time we're trying to connect the ChatGPT kind of, we call LLM. So maybe we will not call LLM afterwards. We can call it a small language model or a medium language model, who knows? We may not call them language models, we can call it image models, small image models or large image models, we don't know. Research is like that, research is not something somebody has given to you, the recipe, eat it. You just think novel and push yourself. All those are actually the, what we call that, platforms. So the platforms, we discussed the platform chapter already, but still I'm just going to tell you must have confused because I'm always showing Amazon here, okay, Amazon there. So whether I talk about a simple platform or talk about training, so they are just like they have this Reliance stores here. They are stores in the cloud. Okay, you want to do a lot of FPGA computation. Your choice is FPGA, put in your lab. That's the pain. Okay, expensive. It's difficult to even put them together. Sometimes it's really not possible. But you go to Amazon site, everything is available, real FPGA with the virtual front things. So you go, just program it as if you are using it in your lab. Get everything done. Okay. So similarly, I'm giving an example here. Similarly, Amazon or IBM or Cisco, all those big corporates, they provide tons of simulators, servers, computational facilities, even for IoT analysis, complete data analysis framework up there. So all you have to know how to use it. And also online you can find all those process steps, how to use it. So instead of using independently yourself, because as an individual, when you want to have so many tools, you really cannot afford also. Even if you can afford, who will maintain that? Okay, your life, 10 years will go even just setting the background, setting the framework. So rather use those frameworks and get things done. Okay, so you leverage their effort by paying or whatever, okay, and save your own time, your career also. So that's a good scenario, okay. In the beginning, I was kind of very defiant and kind of trying to use them, so I built my own server network, all these fancy things in my lab. Then I found that it make me tired and keep doing that, and sometimes this is a problem. Then my students are struggling to fix it. That's not worth. Okay, so I'll sign those things. Yes, I can. Oh, okay, I'll sit down. Okay.